Welcome back. So today we're going to look at a class of matrix algorithms called iterative matrix algorithms. And we'll see how to implement these in parallel. Okay, so remember from the previous lecture, we talked about solving systems of linear equations, right? So we have the system AX equals B. So A is a dense matrix. It's an n by m matrix, right? And we're trying to solve for these variables X. And we had a method called Gaussian elimination, which could solve this system in order n cubed time, right? N is the number of variables that we have. And we can run this in parallel also. However, it turns out that in practice, we sometimes need to work with very large A's. Okay, so so the A can have millions of variables or more, right? So in that case, since we have this, the amount of work for Gaussian elimination is n cubed, then even if you run this in parallel, it's going to be way too slow for very large matrices. Okay, so what we need is we need some faster algorithms to solve for these equations. And what we're going to see today is that we're going to look at first of all some certain types of structured matrices. Okay, so what are called banded matrices. And we'll see that for these special matrices, we have these iterative solution methods, right, which can help us solve this AX equals B much more quickly. And in general, if we have general sparse matrices, okay, then we can use these iterative algorithms to get approximate solutions to AX equals B. Okay, so we're not going to find an X which has exactly AX equals B, but we're going to find x's where AX is very close to B. And the reason these are called, so these are approximate solutions, and the reason these algorithms are called iterative is because we're going to create these solutions step by step. Okay, so we're going to initially start with a very poor solution, right? Some initial X vector, okay? And then we're going to do these iterative algorithms, and then that's going to improve the quality of the X vector. Okay, so AX is going to get closer and closer to B the more times we iterate this process. And eventually, we want that we want the X's that we produce to converge to the right solution. Okay, we want that eventually AX is exactly equal to B. Okay, so the way we're going to do this is, so let's let A be an n by m matrix. Right? We're going to write A as m minus n, where m and n are also two matrices, two n by m matrices. Okay, and the first requirement is that we want we want the inverse of m to be easy to compute. Okay, so for example, if m is a diagonal matrix, okay, then we can easily compute its inverse, right? Because it's just the inverse of all the diagonal elements. Okay, so we're going to split A in this way, and we want m inverse to be easy to compute. And now suppose you have a solution to AX equals B. Okay, so let's let this be X star. Then since A equals m minus n, then just plugging that in, we have that m times X star equals n times X star plus B. Okay, so now we're going to define this matrix C over here. Okay, so C is going to be equal to m inverse times n, right? So remember that we have m inverse is easy to compute, so therefore we can also easily compute C. Okay, and then D is going to be m inverse times B. So D is a vector, right? Okay, so then now if you just if you look at the previous formula here, so what we have is if you multiply both sides of this formula by m inverse. Okay, then you're going to have, we're going to have this, right? So we're going to multiply this by m inverse. And on the left, it's going to cancel. So we just have X star on the left. Okay, and on the right, the first term is going to be, since we're defining C to be m inverse times n, right? Then the first term here is going to be C, right? And then the second term here is going to be D. So therefore, we have that X star is going to equal C times X star plus D. Okay, so now the way we're going to run this iterative algorithm is that we're just going to repeatedly apply this formula over here. Okay, so what that means is that initially we're going to start with some value, some vector x0, let's say. Okay, we're going to plug x0 into this formula, so we're going to compute C times x0 plus D. Okay, so that's good. That's going to get a new value for x, right? Let's call that x1. Okay, then we're going to plug that x1 into the formula again. So you compute c times x1 plus d. Okay, that gets you a new vector x, which let's call that x2, right? And then you plug that back in. Okay, so you just keep doing this. And then, so let's say that after doing this for k times, you get a certain vector x of k. All right, so then for the next iteration, you're going to compute x of k plus 1, which is equal to c times x of k plus d. Okay, so remember our goal was that as we keep iterating this process, we get closer and closer to the actual solution of the equation, right? So we're trying to solve this equation over here, and we hope that as we iterate this process, we get closer to the true solution x star. Okay, so so the way we can express that is we want to say that the iterates converge. And so we're going to say that as you take k to infinity, right, then x of k eventually converges onto the correct solution x star. Okay, and this x star solves this equation over here. Right? And then once you get this x star, right, then we have that x star also solves this original equation. Right? So we have a of x star, a times x star equals b. Okay, so then how do we know whether, these iterations do not converge under all conditions, okay? So we need some special situations in order to guarantee that these things converge, okay? So how do we, what are the criteria that can ensure that these iterations converge? Okay, well, the way we're gonna do this is, let's first of all write that, so we have that x of k plus 1 equals c times x of k plus d. Okay, so now if you subtract x star from both sides, okay, so then what you get is that, so on the left here, you get x of k plus 1 minus x star, okay, and this equals, if you subtract x star over here, right, it equals this, okay, but you see that d minus x star, okay, so suppose we subtracted x star over here, okay, so if you do d minus x star over here, right? And then suppose you move, the c times x star to the other side, okay? Oops. Right, so you see that d minus x star, right, this term over here is equal to c times x star. Okay, so therefore this term here is, so we have this is equal to c times x star, right? Sorry, this is negative of c times x star. And so this is equal to negative of that. Okay, so then you factor out the c, and you get that the right-hand side is equal to c times x of k minus x star. Okay, so we have that the left-hand side is going to be x of k plus 1 minus x star, and this equals c times x of k minus x star. Okay, so this gives us some relationships between these between the convergence. Okay, so basically what we're looking at is we want these x of k's to eventually converge to x star, right? So then here on the left-hand side, this is like the error in x of k plus 1, okay? Because you're just subtracting x of k plus 1 minus x star, right? And then this is saying that the error in the k plus first iteration is equal to c times the error, right? So this is the error in the kth iteration. So it's equal to c times the error in the kth iteration. Okay, so that's what this formula indicates. And now you can also, so here, k can be just any value. So therefore, if you, we can just do the same process, and you can also get that the error in the kth step, right, is equal to c times the error in the k minus first step. Okay, and in general, if you do this for k times, what you see is that the error in the kth step, right? So each time you do this, you're going to multiply by another factor c over here, right? Because here error in the k plus first step is equal to c times the error in the kth step, which is equal to another c times the error, and this thing over here is equal to c times the error in the k minus first step. Okay, so each time we expand these terms, right, we get that the error is equal to eventually we get that the error is equal to c to the kth power, okay, times the initial error, right? So this is the initial vector that we started with, right? So this is the initial error in that vector times c to the kth power, okay? And if we want things to converge, we want this to eventually go to 0. Okay, so then how do we know whether this goes to 0? Okay, well, it depends on what happens with the C over here. Okay, so now if you let a row of C, okay, be so we're going to compute the largest eigenvalue of C, and let's let rho of C be the magnitude of that largest eigenvalue. Okay, so then we have this theorem, right? So basically the theorem says that if the largest eigenvalue, if the magnitude is less than 1, okay, then these iterates are going to converge. Okay, in other words, so if the magnitude here is less than 1, right, then c to the kth power, if you take that to the limit k approaches infinity, then this is going to be 0. Okay, and if this is 0, right, if this term is 0 over here, then that means that eventually these iterates are going to converge onto the correct solution. Okay, and furthermore, this happens for any initial x, right? Because if this is 0 over here, then it doesn't matter which x you start with, right? Any x is eventually going to converge to the right solution. Okay, so this is the basic iterative method. Okay, we're gonna take a matrix A. You're going to break it into 2 parts, m and n, right, where m inverse is easy to compute, right? And then you want to make sure that this this matrix C over here, which is equal to m inverse times n, right, you want to make sure that this guy has a eigenvalue, the largest eigenvalue is less than 1 in magnitude. Okay, if this is true, then you can run the iterative algorithm and you can get the solution. Now, we're going to decompose A equals m minus n, okay? But I haven't specified what m and n are, right? The only requirement is that m inverse is easy to compute. Okay, but there could be different matrices, different m's where their inverses are easy to compute. Okay, so which m and n are we going to use? Right, so now depending on the m and n you use, we're going to have different iterative algorithms. So the first iterative algorithm is called the Jacobi method. Okay, so here we're going to take this matrix A, and you're going to write this as the 3 terms. Okay, so the D term here is just going to be the diagonal elements in A. Okay, so we have a matrix A over here, right? So we have some diagonal elements. Okay, and that's the D term. Right. Now below the diagonal, you also have some elements. Okay, so let's call that L. Okay, and then above the diagonal, you have some elements. Let's call that R. Okay, so then L, or negative L rather, is going to be the lower triangular part of A. Okay, so we're going to take away D, and then if you look at the lower triangular part, right, that's going to be negative L. And then the upper triangular part, right, that's going to be negative R. Okay, and now we're going to set M to be just the diagonal elements. Right, and then for N, we're going to set that to be equal to L plus R. Okay, so in that case, we have that we have A equals M minus N, right? And then also, we wanted to make sure that M inverse is easy to compute, and this is true in this case because if you just set M to the diagonal elements, right, then we can easily compute the inverse, right, just by taking the inverse of all the diagonal elements. Okay, so now we have that C equals M inverse D, M inverse N, right? And so that's just equal to D inverse times L plus R, okay? And then this vector here, D, is equal to D inverse times B, okay? Now, we can actually compute this C matrix explicitly because if you look at the ijth entry, okay? So if let's say this is the matrix A over here, right? And let me draw A again, right? So if you take the ijth entry, okay, then if it's let's see, so if it's on the diagonal, okay, then notice that this L plus R has only zeros on the diagonal, okay, because we've taken out the because the way you form A is the way you form these L and R is that you don't include the diagonal elements. Okay, so L plus R has zeros on the diagonal. Okay, so all these CIIs are going to be 0. Okay, and then off of the diagonal, right, then you just have that the C matrix is exactly equal to the A matrix. Okay, so then in the ijth position, right, of C, you just have that this is equal to negative Aij. Okay, and now you want to multiply this by I'm sorry, in the so before you multiply by D inverse, okay, in the ijth position of L plus R, you have that this is equal to Aij, negative Aij, right? And then once you multiply by D inverse, right, then we know that D inverse is simply the inverse of all the diagonal elements. Okay, so if these are the diagonal elements, right? So if we have like 1, 3, 2, right? Then the inverse is just going to be, it's going to be 1, and, right? And then 1/3, right? And then 1/2. Okay, so each of these, so when you multiply by D inverse here, you simply divide by the diagonal elements of A. So therefore, the ijth element of C is just going to be negative Aij divided by Aii. Okay, and that's for all the non-diagonal elements. And then for the diagonal elements, it's all going to be zeros. Okay, and then for D, right? So D here, you just divide by all of the diagonal elements of A, right? Because again, D is simply the inverse of all those diagonal elements. Okay, now it turns out that if we so we have these conditions to guarantee convergence, right? Well, it turns out that if you have this condition over here, okay, if the diagonal elements, so for each diagonal element, okay, Aii, okay, if you take all of the other non-diagonal elements, and if Aii is actually larger than the sum of all those non-diagonal elements, okay, their absolute values, then we have that we can guarantee the iterative process is going to converge. Okay, so in that case, we say the matrix is diagonally dominant. Okay, so if you have that the diagonal elements are very large compared to the non-diagonal elements, then the matrix is diagonally dominant, and then it's guaranteed that the iterative algorithm will converge. Okay, so now now let's try to run the iterative algorithm. Okay, so the basis for the iterative algorithm is that we need to keep using this formula over here. And so the way you do this is, well, now we know all of the values, the components of C and also D. Okay, so we're just going to plug those into this formula over here. All right. So now, so we've already computed this x of k. All right. So we're going to take these components of x and k, and we're going to multiply this by C and then add D to it, and then we're going to see what we get. Okay. So in particular, if you look at x of k plus 1 and you look at the ith component of that, okay, what you see is that, well, you simply need to take, let's see, how do I represent this? Okay, so let's say that this is our C matrix over here, okay? Right, so let's erase all this other stuff, right? And then you need to multiply it by this x of k, or x of k, right? And so, yeah, so we're just going to go through a row of C and then multiply by this x of k over here, all right? So in general, if you're in the ith row, right, then if you look at these values for the ith row, right, so these formulas tell you exactly what values are in the ith row of C, okay, you see that when you do this multiplication, you're going to get that, so this part over here is going to be equal to C times x, x of k, right, this part over here, right, and then this part over here, right, divided by the Aii, this is going to be equal to the ith component of D. Okay, so therefore the ith component of x of k plus 1 is going to be equal to this. Okay, now the reason you have a j not equal to I over here is because remember that the diagonal element of C is actually 0. Okay, so we add up the entire ith row of C, right, except for we skip over the diagonal element. Okay, now if you look at this formula, okay, you see that in order to compute the k plus first value of x, okay, the k plus first iteration of x, okay, all you need are the values from the kth iteration of x, right? So yeah, so x of k plus 1 only depends on values from x of k, right? And also you notice that different coordinates of x of k plus 1, okay, they don't have any dependencies on each other, because for example, this coordinate, right, the ith coordinate, this only depends on values from the ith row of C. Okay, and so every coordinate of x of k plus 1 depends on a different row of C. So they don't have any dependencies on each other. Right. So therefore, if we've already computed x of k, right, then since that's all we need for x of k plus 1, And since all of these coordinates don't have any dependencies, then we can compute all the components of x of k plus 1 in parallel. Okay, so yeah, so before we give the parallel algorithm, let me just show you like an actual example of doing this Jacobi iteration. Okay, all right, so the basic formula that we have over here is, so this is just a formula from the previous page. And if you want to apply this on a concrete example, then suppose you have this matrix A over here. Okay, now this matrix A is diagonally dominant, okay, because these diagonal values, right, are larger than the sums of all of these non-diagonal values. Okay, so then the way that you form, the way you do the Jacobi method is you're going to take all of these diagonal elements, right, and then you're going to take away all of these diagonal elements, okay, right, so you can take away the 10, 11, 10, and 8, right, and so that leaves you with all of the non-diagonal elements, and then you're going to multiply that matrix, okay, so here we've taken away the diagonal elements, right, and then you multiply that matrix with x, okay, and that gets you the next iteration of x. So, so for example, if you start with x as all the x being all zeros, right? Then if you multiply by the L plus R matrix, right? Then you're gonna get this thing over here, right? And then if you divide by these diagonal elements, right? Then you're gonna get these values over here. Okay, so that's one iteration of this iterative algorithm. Right? You start with all zeros, and then you get a new estimate for x. Okay, and then you can plug this into the overall equation, and you can see that when you use this x, right, you get a much closer solution to this overall equation than when you use this initial value for x. Okay, and then for the next iteration, you would plug these values into this formula over here. Okay, and then that'll get you some new values for x, which will be an even better solution. Okay, so now let's see how we can actually run this Jacobi method in parallel. Okay, so so since all of these components of x of k plus 1 are independent, we can use up to n different processors to run this. Okay, so when we do this, so let's say that you actually use p processors. Okay, so p can be as large as n. So the first thing is, how do we distribute the matrix among these p processors? And we're just going to use the traditional row-wise block format. Okay, so if you have a matrix like this, right, and if you have p processors, we're just going to break the matrix into chunks of n divided by p rows each, and then you give each chunk to a processor. Okay, so here, so this is going to be an m by m matrix, right, and then each of these chunks is going to have n divided by p rows in it. Okay, and likewise, you're going to break the b vector also into these into n divided by p entries each. Okay, now the way this code is going to work is that it's going to compute. So x of k plus 1 is going to be called x new in this code. Okay, so this is MPI code over here, and I'll go through this in more detail soon. Okay, but let's first look at it at a high level. So x of k plus 1 is x new, and x of k is going to be called x old. Okay, so now in order to do this operation over here, okay, to do one iteration of the Jacobi method, you see that each processor needs all of the values of x. Okay, and so what we're going to do is, let's see. Okay, so n local is the number of rows that each process has. Okay, it's equal to n divided by p. Okay, so we have the old. Sorry, we have. This is going to be the new value that we're trying to compute for x, and this is the old value for x. And so what we are doing is that for each of the rows that we have, okay, so each process will be responsible for n divided by p coordinates. Okay, so each process has n divided by p different values of I that it's trying to apply this formula for. Okay, and then so here in this loop, we're just applying this formula. Okay, so the I global here is going to be sort of the row that the process is working with. Okay, so for example, if there are let's say there are 50 rows, let's say n is equal to 50. Okay, and let's say you have 5 processes, right? Then each process is going to have 10 rows, and so n local here is going to be equal to 10, right? Me, this is going to be the ID of the process. Okay, so if we're talking about process 2, right? then if it's working on its, let's say, first row, right? So then that actually corresponds to, so that corresponds to the 21st row overall, okay? Because since we're working on process 2, then the previous 2 processes already received 20 different rows, okay? So the first row for process 2 is actually the 21st row overall for all the processes. So that's what we're computing in this iGlobal over here, right? Now this part, this line over here is just so you notice that the first thing we need to do is we need to do bi divided by aii, okay? So this part over here is copying the b's into the into this local x vector over here. All right, and then next we're gonna do this. We're gonna do these for loops. Now the for loops correspond to 2 parts. So you have this overall sum over here, right? So the sum actually goes from 1 up to I minus 1, right? Okay, and then it goes from I plus 1 to n, okay? Because we want to skip over coordinate I over here. Okay, so the first part of this for loop just sums all the values from 1 to I minus 1. Okay, so you see that we're going to take this b value, right, and you're going to subtract the part of the A matrix that we have multiplied by the old value for x, right? The old value for x in the jth coordinate is going to be this x of k sub j, right? Okay, so we do that for the first part, right? So that's the first for loop over here, and the second for loop just goes through the other part also. Okay, and then after that, right? So after we've done both for loops, we've actually computed this this entire sum over here. Okay, now the final thing to do is just to divide by a of ii. Okay, so then here we divide by this thing. Okay, and the reason we're using the global so here the first index is our local row, right? So if we're working with row 1, right, then yeah, we're going to use a 1. Okay. But you know, the actual row globally in the matrix, in the A matrix that we're working with is, let's say, actually 21. Okay, so we need to go look in column 21 and then the first row of our local A matrix. Okay, so then after doing this entire, let's see. Okay, so after doing this entire for loop over here, okay, then each process is going to end up with n divided by p values of this x of k plus 1. Okay, he's going to end up with n divided by p coordinates of this x of k plus 1. All right. And now we want to just send this entire vector x of k plus 1 to all of the processes. Okay, because right now they only have part of x of k plus 1, but we want all the processes to have all of x of k plus 1. Right. So to do that, we're just going to use this mpi all gather command over here. Okay, so this all gather is going to take, each process is going to take its local chunk of x of k plus 1, and it's going to sort of send it to all of the other processes. Okay, or you know, alternatively, you can say that each process is going to get, you know, a chunk of x of k plus 1 from each other process. Okay, so that's what we're doing. And then we're, so because this is an iterative algorithm, right, then we're going to keep doing this process. Okay, so each time we do this process, we compute the next iteration. Okay, now when do we stop, right? Because you don't want to do this forever, right? So you stop when either you've run for like some maximum number of iterations. Okay, so let's say you only want to run for 100 iterations. Okay, or you stop when x old and x new are very close to each other. Okay, so if you have x of k plus 1, right, and x of k are very close to each other, right, then you can also stop, because at that point you converged. Okay, so that's how you do this Jacobi algorithm in parallel. All right, so now we're going to talk about a new algorithm, it's basically a modification of Jacobi's algorithm. Okay, it's called the Gauss-Seidel method. The Gauss-Seidel method is going to converge faster than the Jacobi method. And the way it works is, again, we're going to write A as equal to the diagonal elements minus the lower triangular part minus the upper triangular part. Okay, but previously we set M to be equal to D. Okay, and now this time we're going to set M to be basically the entire lower diagonal part plus the diagonal. Okay, so again, we have this picture of A over here, right? So we have the diagonal part over here, right? We have the lower part and the upper part. Okay, So now we're going to set m to be equal to this entire thing over here, including the diagonal. Okay, and then n is going to be the upper part. Okay, so then c is going to be equal to m inverse times n, right? So that's going to be equal to d minus l inverse times r. Okay, now d minus l here, right? This is a lower triangular matrix. Okay, so if you're trying to, so we need to be able to compute this inverse quickly, right? But you can do this because d minus l is a lower triangular matrix, then you can use the forward substitution method to compute its inverse. Okay, so forward substitution is basically you solve for this variable first, right? And then you substitute and then solve for the next variable, right? So then you just go row by row like that. Okay, and you can do that when it's lower triangular. Okay, now it turns out that this Gauss-Seidel method, we can also guarantee convergence if the matrix is diagonally dominant. Okay, so the diagonal elements are larger than the sums of all the other elements. Okay, and then also we have that x of k plus 1 is again equal to c times x of k plus d. Okay, now it turns out that so we actually want to figure out all the components of these x of k plus 1. Okay, so we want to write this in component form. So it turns out that by doing some operations similar to the Jacobi method, you can show that x of the ith component of x of k plus 1, okay, is going to be equal to this thing over here. Okay, now this thing is actually very similar to the previous sum that we had for the Jacobi method. Okay, because you see that again to get the to get the value in the ith row, right? We're going to iterate through the ith row of A, right? And then you're just going to multiply by these corresponding elements of x of x. Okay. Now the only difference is that so in the Jacobi method we saw that we broke the sum into two parts, right? First part is from for the j's from 1 to I minus 1, and the other part is from I plus 1 to n. Okay. And in both parts you multiply by this x of k, right? So x of k is what you computed in the previous iteration. Right. Now in the Gauss-Seidel method, we're going to do the same thing basically. Okay, we're again going to take the ith row of A, but now for the first half of the sum, okay, for j from 1 to I minus 1, you're going to multiply by x of k plus 1, okay, which is what you're computing in this iteration. Okay, we're in the k plus first iteration. Okay, and then for the second part of the sum, you're going to multiply that by x of k, which is what you computed from the previous iteration. Okay, so the way this is going to work is we're going to compute these components of x of k plus 1 by one, for I equals 1, 2, 3, and so on. Okay, and so first of all, we're going to compute this for I equals 1. And when you do this for I equals 1, right, then actually you don't have any terms over here. Okay, the only terms are for here over here, right? So we need to add this up for I equals 2 up to n. Okay, for j equals 2 up to n, right? And this is only relying on the values that we computed from the previous iteration, x of k, right? So to compute x of k plus 1 sub 1, we only need values from x of k. So then after you compute the first component, we're going to compute the second component of x of k plus 1. In that case, we actually need to use one component from x of k plus 1, namely the first component. Okay, but we just computed the first component. So therefore, we have this component over here. And then for all the other components, we're going to use the ones from x of k. Okay, so that's going to let us compute the second component of x of k plus 1. Right? And now when you compute the third component of this thing, right, you need to use the first two components of x of k plus 1. But we just computed those, so we have those. Okay, and for the other components, you use x of k. All right, so the basic procedure is that you compute these components for I equals 1, 2, 3, and so on. And when you're at the when you're trying to compute the ith component, right, you need these I minus 1 components of x of k plus 1, but you've already computed those. And so you can just plug those in. Okay, and for the remaining components, you're going to use them from x of k. All right, so now what is the benefit to doing this? Okay, so this is different from the Jacobi method, and the claim is that this Gauss-Seidel method is actually somehow more accurate because it converges faster than the Jacobi method. Okay, now why does it converge faster than the Jacobi method? So intuitively, we're not going to do the sort of the proof of this, but intuitively, what is happening is that in the Jacobi method, right, the sum only used. So let's sort of clear this up over here, right? The sum only used values from the previous iteration, right, from the kth iteration, right, and presumably the kth iteration is less accurate than the k plus first iteration, right? Because as we iterate, we get better and better approximations for x, okay, for x star. Okay, so this Jacobi method is using sort of these inaccurate values for x, for x. Okay. Whereas the Gauss-Seidel method, right, because some of these values are from the current iteration, and this current iteration has produced more accurate estimates for x. Okay, so then here we're using these more accurate values for x. Okay, and then also here we're using some inaccurate values for x. Okay, but at least part of this formula involves more accurate values for x. Okay, and so therefore, since your inputs are more accurate, right, then your output over here, right, is also going to be more accurate, intuitively. Okay, so that's how this is working. Okay, so by using the values from the current k plus first iteration, which is more accurate than the values from the kth iteration, then we can get more accurate values for these components. Okay, and this is what allows the Gauss-Seidel method to converge faster than the Jacobi method. Okay, now the problem with the Gauss-Seidel method. Okay, so even though it converges faster, the problem is that for the Jacobi method, we could compute all of these components in parallel, because all of these components only depended on values from the previous x of k. Right, so as soon as you're done with x of k, you can compute all of the components of x of k plus 1 in parallel. However, for the Gauss-Seidel method, you can't do that anymore, because for the Gauss-Seidel method, right, when you're trying to compute the ith component over here, you need to first compute the up to component I minus 1 in this k plus first iteration. Okay, so that means that for the k plus first iteration, you need to go through these components basically one by one to compute them. Okay, instead of computing all of them in parallel. Okay, so therefore in practice, even though it converges using fewer iterations, right, using a smaller value for k, it might not run faster because you have less parallelism. Okay, so later on we're going to see how to actually apply the Gauss-Seidel method in certain special cases in order to actually get parallelism in those special cases. Okay, but in general, because of these dependencies between the different components of x of k plus 1, then in general we cannot parallelize this process, and so it's not going to be it's not necessarily faster. Okay, now before talking about those special cases, I'm going to introduce one more method, which is called SOR, which stands for successive over-relaxation. Okay, so this is a modification of the Gauss-Seidel method, and it again has improved convergence compared to the Gauss-Seidel method. Okay, so basically, so in the Gauss-Seidel, so the way the SOR method works is that x, each time we iterate, is now going to be a linear combination of the value you get from the Gauss-Seidel iterations and the previous value for x. Okay, so in formula, so to give a formula, what we're going to have is we're going to have these two terms. Okay, so the first big term over here, right, this entire thing over here. Okay, this is going to correspond to the value from a Gauss-Seidel update, right? So you see that this is exactly if you ignore this omega over here, right? If you put a 1 over here, then this is exactly what you compute for a Gauss-Seidel iteration. Okay. However, we're going to add this to a combination of the previous value for x. Okay, so therefore we're going to have this parameter over here, omega, and and this omega is going to be sort of control how much of the Gauss-Seidel update we're going to use versus how much of the previous value we're going to use. Okay, so now so we can set different values for omega, And it turns out that the convergence of this SOR method is going to depend both on the properties of A. Okay, so for example, if it's diagonally dominant or not. Okay, and it's also going to depend on properties of omega. So for example, it's been shown that if A is symmetric and positive definite, okay, and if omega is between 0 to 2, then this method, SOR method, will converge. Okay. All right, so then now in order to parallelize this, right? So this SOR method has the same amount of parallelism as the Gauss-Seidel method, right? Because to compute this part of the SOR method, that can be done completely in parallel, right? Because it only depends on the value from the values from the previous iteration of k, right? And here, right, this is just the Gauss-Seidel method. So therefore, if we can parallelize this part, then we can also parallelize the SOR method. Okay, so then for the rest of this lecture, we're going to look at different ways of parallelizing the Gauss-Seidel method. Okay, so we're going to, so in general, we can do some parallelism, but it's not going to be a highly parallel implementation. Okay, and then we're going to focus on special cases where A has a special structure, and then we can see that in those cases, you can actually get much more parallelism. Okay, but first we're going to start with just in general, how would you try to parallelize the Gauss-Seidel method? Okay, so basically what we're going to do is, we're forced to compute these I components sequentially. Okay, so you have to do I equals 1 before I equals 2, and then you can do I equals 3, and so on. Okay, so then in this code over here, right, we're just going to iterate through the I sequentially. Okay, so the outer loop is just computing these different I values. Okay, and the parallelism is actually going to be for each fixed value of I. Right, so you have this big sum over here. Right, and the parallelism is just going to be that we're going to parallelize the sum. Okay, so for example, if you have, let's say, 1,000 terms over here, okay, because n is 1,000, and then if you have 10 processors, then you can get each processor to add up like 100 components of the sum. Okay, and then after that, you're going to add up all the components. Okay, so that is going to be our parallelism, yeah, and so if you have a big sum over here, then each process is going to take part of the sum. Okay, so that's what's happening over here. Okay, so each process is going to be computing these various indices, and that's going to correspond to the indices assigned to that process. Okay, so if you have like lots of indices over here, right? So you have lots of indices, right? You're going to give the first part to process 1, right, and then the second part to process 2, and so on. Okay. And all of these things over here, right? So the j's are going to be, so each process is only going to compute n divided by p terms out of this overall sum, okay? And so this j is just going to be, if you're the second process, right, you're going to add up this part over here, and you need to get all of those indices, and then take the a, multiply by x, right? And now, I should mention that this x, okay? So this x, depending on the index j over here, it's going to either include a new value for x, right, from iteration k plus 1, or it's going to include some old value from x from iteration k. Okay, so the way this code works, you automatically, the way it works is you only have one copy of x, okay? And so part of x is going to be have the new values, and then the other part is going to have the old values. Okay, so by the time you're in the ith iteration, right, then all of the values before index I are going to be the new ones from iteration k plus 1, and all the ones after index I are going to be these old ones. Okay, all right, and then after that, we're going to gather all of these values onto this. So then we need to, so each process is going to add up some of these values, and we need to add all of them together to get the new value for x of k plus 1 in the ith component. Right, and so to do that, we're just going to first of all compute which node we want to add all these values onto, right? And then we're just going to do a reduce operation over here. Okay, so this is going to reduce onto so we have this root process, and the root is going to change depending on which iteration we're talking about. Okay, And then this root process is going to get this entire sum over here, right? And then it's just going to divide by AII over here, okay? And then that is going to be the new value for x of k plus 1 sub I. And then we also need to know whether when we should converge. So we're going to compute this this delta value over here, which is basically how much x has changed. Okay, so this delta x is how much x has changed. And then we're going to look at in total how much x has changed. So we're going to do this all reduce here. So every process will get to see how much x has changed. Okay, and if x changed a lot, right? So if this global delta is large, then we're going to keep iterating because we haven't converged yet. Okay, and otherwise, if global delta is less than this tolerance, right, then we're gonna converge. Okay, so that is basically the what we're doing. Now, in terms of the speed up, we're not going to get too much speed up over here because each process is only doing n divided by p computations, right? Because it's just doing part of the sum over here, which has n divided by p multiplications and additions. Okay, and then you have to do a communication step because you have to reduce all of these p different values. Okay, so you're actually doing quite a bit of communication for not too much computation, right? Like if n is 1,000 here and p is 10, right? Then you're just doing 100 math operations, and then you have to do some sort of communication. And that communication can easily take more time than your 100 math operations, okay? So probably you're not going to get much speed up unless you have a very large n. Okay, so if n is like, a billion, right? And then you have 10 processes, okay? Then, you're going to do 100 million computations on each processor, and that's probably going to be a lot more than your communication time. And in that case, you actually do get a speed up with this method. Okay, but in general, this is all we can do for the Gauss-Seidel method. So in general, we're not going to get a large speed up. Now next, we're going to focus on some special cases of the Gauss-Seidel method. And for these cases, we can actually get more speed up than in the previous example. Okay, so the case we're going to look at basically is this thing called Poisson's equation. Okay, so Poisson's equation, it's a partial differential equation, and it can describe some physical phenomenon like a potential field. Okay, which can be caused by either mass or so it can be a gravitational field or it can be like an electric field. Okay, so we're not going to worry too much about the physics behind the Poisson's equation. So we're going to look at this equation in 2D. We're just going to focus on how we can implement this efficiently in parallel. Okay, so the way that you can express Poisson's equation is we're going to use this. So we're trying to figure out this phi here. Okay, so phi is going to be a bunch of values. Okay, we're trying to figure out what these values are. So we're going to apply this Laplace operator, right? This little triangle over here, right, to phi, and so the way the Laplace operator works is that we're working in a 2D space, okay, and then phi is going to be a function on this 2D space. So this operator is going to take the second derivative of this function in the x direction and then add it to the second derivative in the y direction. Okay, so let's say that you have this part of the 2D space over here, and let's just sort of focus on some region, let's say from 0, 0 up to 1, 1. Okay, so we're just focusing on the square region over here. Right. Now, what we're saying is that if you apply this Laplace operator, so suppose you actually know a bunch of values. You have this function f defined in this range. Okay. Now you want to find phi such that when you apply this Laplace operator, you actually get f. Okay, so f is our input, and we're looking, we're trying to find this phi over here. Okay, such that the Laplacian operator on phi is equal to f. So the way we can do this is we're going to discretize the space. Okay, so initially it's a continuous space, but we're going to discretize it. And we're going to split this into like an m plus 1 by m plus 1 grid. Okay, so there are going to be m plus 1 points over here, right? And there's n plus 1 points over here, okay, for some n. And then h is going to be the size of each of these little squares that you form. Okay, so h is going to be basically 1 divided by n plus 1. And now we're going to say that at each position in this grid, okay, at position ij, we're going to let u of ij be the value of phi at that position. Okay, so yeah, and then we're going to let f of ij be the value of f at that position. Okay. Now, once you have this, it turns out that, so now we want to express this Laplace operator in terms of these values, u and f, okay? And it turns out that, so the Laplace operator has second derivatives, right? So you know that if you have first derivatives, then the way you can express like a derivative is something like, well, a derivative would be, we want to take, let's say, the value of u at this point, right? So that's the value of phi at this point. And then if you subtract the value of u at this point, right? And then if you divide by h, okay? So we have, let's say, u of I plus 1, j, right? Minus u of ij, okay? Oops. And then you divide this by h, right? So now this is going to be approximately equal to the derivative of phi, right, with respect to x at this point ij, right? Because it's just an approximation for the derivative. Okay, so but for the Poisson equation, we actually want the second derivative. Okay, now it turns out that you can use a very similar method, and you can express the second derivative over here. Okay, and also the second derivative in y. And then if you do that, right, you're going to end up with an equation like this. Okay, so just like over here, you can write this in terms of the u values, right? You can also write the second derivative in terms of the u values. Okay, and then you want this to be equal to the value of f at this location. Okay, and you want this to hold for all the points, for all ij from 0 to n plus 1. You want this to hold. Okay, so that means that you have a bunch of these equations over here. Right? For each value of I and j, you have one of these equations. And these are linear equations. Right? So we're given the values f, right, because that's part of your input. And we're trying to find the values of phi, and that just involves finding all of these u values. So this means that we've now expressed Poisson's equation as a system of linear equations. Okay, and now we're going to go solve those equations using the Gauss-Seidel method. Okay, so before we do that, let's just suppose that we're going to fix the value of phi on the boundary of this. Okay, so the boundary is going to be these locations over here. We're going to fix the boundary of this, and then so here you have to divide by this term 1 minus h squared. Okay, because you're doing a second derivative, so it turns out to be an h squared. And so let's just sort of take out this term so that we don't have to keep writing it later, okay? So we're going to divide out both sides by 1 over h squared. Okay, and now since we fixed the value of phi on the boundary, we're going to look for the value of phi in the interior of the square, okay? And that's going to lead to a system of n squared linear equations, okay? One for each I from 1 to capital N. Okay, so then how do you solve these equations? So we're going to let x of k, so we have a bunch of these unknowns, right? So these unknowns have two indices, which is kind of hard to work with. So instead, we're going to just convert these to a single index, okay? So yeah, so what you're going to do is you're basically going to label all of the x values, you're going to label these u values in this order. Okay, so the indices are going to work like this. So it's going to be a row major ordering of all of these points in the square. Okay, so in general, you're going to have that, oops. Oh, okay, right, so in general, okay, let's do this a bit more slowly. All right, fine. So everything shows up at once. Okay, so in general, point uij over here is going to get converted to this index k, where k is going to be equal to the row plus the column times n. Okay. All right, and then now we can so we have these we have this equation over here, and you see that basically for each equation you have only five non-zero values over here. Okay, 5 non-zeros in the coefficients, right? So what that gets converted to is if you look at a why is this so slow? Okay, so if you look at a picture of this, okay, so for so here we have n squared unknowns that we want to solve for in total, right? Because we have n squared different values of uij. Okay, so now we're going to make an n squared by n squared matrix, right? So we're going to set this little n here is actually going to be equal to capital N squared. Okay, so now we're going to write, we're going to show exactly where the non-zeros in this matrix are. Right, so this picture shows where the non-zeros are. Okay, so in general, you have from the previous page, you have that we're trying to solve this equation. Okay, so this right, so you see that for example, the this thing over here, right? This is going to be x of k. Okay, so in that case, we have that this is going to be x of k minus 1. Okay, and then this is going to be x of sorry, this is going to be x of k plus 1. This is going to be x of k minus 1. And then now these two things, okay, these two things are in a different row. Okay, so so instead of just being x of k plus 1, right, this is actually in x of k plus the next row, right? So each row has n elements. Okay, so this is actually the next element in the next row. Okay, and this is the element in the previous row. Okay, x of k minus n. Okay, right. Okay, so then let's go back to the this formulation over here, right? So this is how you get this equation over here. Okay, this is again u of ij. This is u of I minus 1j, and so on. Okay, and this bk over here, right? This is so we said that we're just going to take these f of ij's, and you're going to divide out by the by 1 of h squared by 1 divided by h squared. Okay, so that's where you get these b values from. Okay, so we have these equations, right? And now we're trying to solve them. And so if you look now, let's first of all look at where the non-zero values in this equation are. Okay, so as I said, for each value of k, right, we have only 5 non-zeros. Okay, we have a non-zero here, and then for this, and then for these. Okay, so if you look at how this works, then for example, if you have an x of k over here, okay, so then you have a non-zero in the previous index k minus 1. Okay, you have a non-zero in the next index k plus 1. And then you have another non-zero, which is in the index k minus n. Okay, so that's what's being shown over here. And then actually there's also going to be a non-zero over here in the index k plus n. Okay, so every row is going to have 5 non-zeros. And if you look at all of the rows, right, then you see that the non-zeros are actually going to lie on only 5 different diagonals. Okay, so the main diagonal is just corresponding to these terms over here, right? And the next diagonal over here, that's corresponding to the k minus 1 terms over here, right? And the k plus 1 terms are these upper diagonals. And then these two things are the k plus n and k minus n diagonals. Okay, but overall you have 5 diagonals for this entire matrix. Okay, all right, so now we're going to apply the Gauss-Seidel method for this in this case, okay, to solve Poisson's equation. So here I've rewritten the Gauss-Seidel method, okay? And when you apply this to Poisson's equation, you're going to get this, right? So here I'm just plugging in these values over here, right? Okay, so now let's look at this sort of pictorially, okay? So what we've done is we took the grid, and then we're saying that for every grid point, this corresponds to one of our unknowns, okay? And now, so then in that way, you get n squared unknowns. However, you can label these unknowns in any order, okay? So we have a grid of points, right? Each one of them is a unknown, but you can sort of order them however you want. So for example, we can order the unknowns in this row-wise fashion, okay? You can also have other labelings. So we'll see that other labelings are going to have different properties. But the first labeling we're going to, first ordering we're going to have is that we're just going to label these unknowns row by row. Okay. Now, if you do this, right, then what you see is that, yeah. So we're going to place these x values on the grid, and then you see that. let's see. Okay. So then we have these dependencies between the variables. Okay. So for example, this variable, right? When you solve this, right? When you want to compute the this variable in the k plus first iteration, right? You need two values from the k plus first iteration, and then you also need two values from the kth iteration. Okay. Now the values from the k plus first iteration, those are dependencies. Okay. So now which two values do we need from the k plus first iteration? So here you can see that we need the one which is to the left of us. Okay, if you look at this coordinate over here, this is a value that's to the left of us. Okay, and we also need the value that is in the previous row. Okay, and that's going to be directly above us. So therefore, for example, for this 8 value over here, right? In order to compute x of k plus 1 sub 8, you need to have x of k plus 1 sub 7, right? And you need to have x of k plus 1 sub 2. Okay? And so in general, whenever you look at a node, okay, it's going to be dependent if you're trying to compute the k plus first iteration value for that node, right? You need to know the value of the node in the k plus first iteration for the node above and to the left. Okay, so that's what the dependencies are. Okay, so if you draw out the dependencies, you have these this sort of grid of arrows over here. Okay, this shows all the dependencies that we have in the computation. Okay, now we've actually seen this sort of configuration before. So if you have dependencies of this form, okay, then you cannot parallelize across the rows or across the columns, right? Because if you, for example, if you try to parallelize across the rows, right, then you know, you're going to have to, so each row cannot be computed in parallel because of these row dependencies. Okay, and likewise for the columns. Okay. However, we saw that you could parallelize if you look at this in a diagonal fashion. Okay, so we talked about this loop skewing method, and if you skew this loop so that you look at it diagonally, then all of these elements on each diagonal can be parallelized. Okay, so for example, if you take this diagonal over here, okay, with the 4, the 9, the 14, and the 19, right? So the only elements that they depend on are these values, the 3, the 8, and the 13. Okay, so if we've already, so if you compute this diagonal by diagonal, okay, then in the previous iteration, we computed the values at points 3, 8, and 13 for iteration k plus 1. Okay, and then for the next diagonal, right, we're going to compute the values for 4, 9, 14, and 19, and that's only going to use the values for iteration k plus 1 on these 3 points. Okay, so once you have those, then you can do all of these computations, the 4, 9, 14, and 19, in parallel. Okay, so in general, this is what we're going to do. We're going to break things up into diagonals, right? And then we're going to compute each diagonal in parallel. Okay, but we're going to proceed through the diagonals sequentially. Okay, so so in total, we have 2 times root n minus 1 diagonals. Okay, if it's a root n by root n grid, right? So remember that n here is actually equal to big N squared. Okay, so then we actually have 2 times root n minus 1 diagonals, and then each diagonal has at most root n points. Okay, and we can parallelize across all of the points on a diagonal, and so therefore we can actually get pretty large parallelism on many of the diagonals. Okay, so we want to, so each of the diagonals, let's say, has L points. Okay, now the different diagonals actually have different numbers of points, right? So so the number of points initially increases, right? So you have 1 point and then 2 points and then so on, but then eventually they start to decrease. Okay, so there are sort of like 2 phases to these diagonals. They first get larger and then they get smaller. Okay, so when you look at this, we're going to say that in the first phase, these are going to be the indices of the points that we need to look at. Okay, so you can like check this computation, but these are the indices for the diagonals that we're going to look at for the first L diagonals. Sorry, for the first root n diagonals. Okay, and then for the other indices for the second phase of this, when the diagonals are getting smaller, right? These are going to be the indices for the points on those diagonals. Okay, so now we can parallelize this guy. And what we are going to do is, well, we're just gonna, so we have these two phases, right, when the diagonals get bigger and then smaller. So we're gonna split that up into two for loops, okay? So the first for loop is gonna be, let's see, yeah, so the first for loop, this is when the diagonals are getting larger, okay? And then within each diagonal, we have a bunch of values, and we can compute those values in parallel using P processors, okay? So this, what this is showing is that each processor is going to compute every pth value, okay? So if you have like 10 processors, you're going to do that, let's say the first value, the 11th value, the 21st value, and so on, okay? And then for each of these values that you're computing, right, you're going to compute the index over here, right? And then you just have, you see that each of these things involves 4 terms, okay? So there are just 4 non-zeros over here. And so that's what's being computed over here, right? So we have these, you know, we have 1, 2, 3, 4 terms over here, right? You have to check that, you know, these array indices are actually within the bounds, okay? So they're not too big and too small. But otherwise, you just add, you know, the A value from the matrix times the previous x value, okay? And then you add that to your b value, and then you divide by the diagonal value, okay? And again, this is for the first phase, right? And then this is for the second phase when the diagonals get smaller. And these, right? And then these collect elements functions, right? They just sort of collect these values, and then just so this is some sort of communication function where you collect these new values that you computed, right? And then you distribute these to your neighbors. So for example, over here, right? So after you compute, let's say this value, right? You need to distribute this to your neighbors so that they can use them for the next diagonal. Okay, so that's what's being done in this collect values, collect elements. Okay, so yeah, and then sorry. And then we're going to repeat this process until everything converges. Okay, so that's what this thing over here is. Okay, so so we saw with the diagonal method that you can get a pretty large degree of parallelism. Okay, but the problem is that since you depend on these diagonals, and since in the beginning the diagonals are very small, right? So the diagonals are small, and then they get larger, and then they get small again. Okay, so at the beginning and end of this process, you actually have very little parallelism. Okay. So now we're going to switch to, we're going to look at a new method for solving the Poisson equation, and this is going to be based on a different way of ordering the points. Okay, so so to see how this works, now we know that in the Gauss-Seidel method, when you're computing the ith component of x of k plus 1, right? This is going to only depend on x of k plus 1 for components j less than I. Okay, if j is larger than I, then we don't need the value from x of k plus 1. We only need it from x of k. Okay, so since we're always computing these things in the iterations, like, you know, k and then k plus 1 and then k plus 2, then you know, when you're computing x of k plus 1, you have all of the values for x of k. So the only things you're worried about are these x of k plus 1 values for j less than I, okay? And if aij is not equal to 0. Because if aij is equal to 0, then, of course, you know, when you multiply this aij value by x of j, you that's 0. Okay, now the key to the red-black ordering is that, so previously when we ran the diagonal method, right? So we order the points in this sort of natural way over here, right? Sort of in this row major ordering. But the thing is that you don't have to order points in this order, right? You can actually order the points any way you want, right? So you know, what I'm saying is that here we're calling this point x1, okay, and this point x2, and so on, okay? You don't have to call the points, you don't have to order the points that way, okay? You could do something else where maybe you call this point x1, and maybe this can be x2, and this can be x3, and so on, okay? So in fact, the red-black ordering is going to reorder the points, and it's going to do it this way. So it's basically going to create a checkerboard pattern on the points, okay? Red-black checkerboard pattern. So what that means is that each of the points, we're going to think of it as either a red point or a black point. Okay, and the first point, let's say, is going to be a red point. Right? And then so all the red points are going to be sort of skip one from the previous red point. Okay, so this is going to be the first red point. That's the second point, right? That's the third point, 4, 5, and so on. Right? So those are all the red points, and then we're going to order all the red points before all of the black points. Okay, so here there are 24 points in total, right? We're going to order 12 red points, and then we're going to have these black points. Okay, 13, 14. Okay, so overall, this is going to form this checkerboard pattern over here. Okay, so now this is going to be x1, and this is going to be x2, x3, and then this guy here is going to be x13. Okay, and what we're going to see is that using this checkerboard pattern, then we're going to have far fewer dependencies, right? And then we have a lot more parallelism. Okay, so in fact, what you can kind of see from this is that now each point xi is only going to depend on the points xj for j less than I. Okay, and what you can see over here is that, for example, this point x4 over here, right? So it only depends on x13 and x16. Okay, sorry, and then also x17 and x19. Okay. But all of these points, right, 13, 16, 17, 19, they all have j, which is larger than 4. Okay, so x4 of, let's say, k plus 1, iteration k plus 1, okay, depends on x, what do we have here? 13, right, x17, 16, 17, and then 19. But this is all for iteration k. Okay, because all of these indices over here are larger than 4, right? And we know that if your index is larger than 4, then you only care about the value from x of k. Okay, you see that this point 4 over here, it doesn't have any dependencies to the red points, and the red points are the only ones with indices less than 4. Okay. All right, so what this tells you is that you can actually compute all of these red values, okay, in parallel. Because if you take any red value, it only depends on black values. And the black values have higher indices than the red values. So since they have higher indices, you only need their values from the kth iteration, not the k plus first iteration. Okay, so you can do all of the red points in parallel. All the red points for iteration k plus 1 in parallel. And then after you've done that, right, now let's look at the black points. So the black points are only going to depend on the red points. Okay, and since you've already computed all of the red points for iteration k plus 1, right, then when you want to compute this black point, right, it needs the values for iteration k plus 1 from the red points 2, 4, 5, and 8. But we already have those because we just computed, because you compute the red points for iteration k plus 1 first before you do the black points. Okay, so the black points can also be computed in parallel, right? Because all the red points have been computed already in iteration k plus 1. So therefore, you see that using this red-black ordering, you can compute all the red points in parallel. So that's like half of all the points you can do in parallel, right? And then the other half of the points you can also do in parallel. So this gets you much better parallelism than the diagonal method, right? The diagonal method, at most, you could parallelize across the largest diagonal. Okay, so that's like sort of square root of the number of points. But here, for the red-black ordering, you can parallelize across half of the points. Okay, so so we can show this another way, which is that we can actually write out the A matrix, right? So so what are the non-zero values for the A matrix? Well, so because you don't have any dependencies between the red points, okay, then what I'm showing over here is that I'm listing all of the red points before all of the black points, right? That's what we said we're going to do, okay? And since you don't have any dependencies between the red points, right, then the only non-zeros in the A matrix are on these diagonals. Okay. Now you do have some dependencies between the red and the black points, and that's what these other parts are. Okay. But as we said, we can first of all compute all of the red points for iteration x of k plus 1 in parallel, right? And then we're going to compute all the black points for x of k plus 1 in parallel. Okay, so to see sort of to sort of write out some equations for doing this, right? Let's actually label these different parts of the matrix. Okay, so we're going to label this. This is going to be the red points, right? And so this is going to be a diagonal matrix or submatrix, and so we're going to write this as d of r, a d sub r. Okay, and this is a these are the black points, right? This is also diagonal, so this is going to be d sub b. Okay, and these other parts, right? So this part here is going to be E, and this is going to be F. Okay, so then, we're also going to write the vector this way. So we're going to label all the red points before the black points. Okay, so now what we're trying to do is now the diagonal. So we have the A matrix this way, right? So the diagonal of the A matrix are just going to be these red and black diagonals. Okay. So the L matrix, the lower triangular part, is going to be negative of this E part over here, right? And the U is going to be negative of the F part. Okay. So now we can write the Gauss-Seidel iterations. So the so the Gauss-Seidel iteration is we're taking D plus L, right? And then you're multiplying by this by the X vector, right? And then this is going to be equal to this B value minus the upper triangular part times the X vector from the previous iteration. Okay, so then what you see is that when you do this out, you see that in order to do this multiplication, you see that you have a dr, right? Dr times the red diagonal elements times the red points in iteration k plus 1. Okay, and this equals b1 minus, here you have the f times the black points from iteration k. So we have this formula over here. Okay, and also you have that. So here, if you multiply the second row, right, you have e times x r of k plus 1, right, plus d times the black points for iteration k plus 1 equals this b2 here minus what do we have here? Minus, well, nothing. Okay, so this is, yeah, and then so if you rearrange this, you get this expression over here. Okay, and so this holds for all the k, right? And so so you see that here to compute the red points for iteration k plus 1, we're only depending on the black values for iteration k. And then to compute the black values for iteration k plus 1, we're only depending on the red values for iteration k plus 1. Okay. All right, so so this is how we're going to proceed. And to sort of write this out in coordinate form, or sorry, in components form, right? So you can actually write out these components. So what this is saying, so this n of I is just going to be the neighbors of point I in the grid. Okay, so it's the points to the left and the right and above and below. Okay, so then we have this equation for the red points, right? You're going to compute all of those, and then you have this equation for the black points, right? And you compute all of those. And here you need to add, so n of r, n sub r is going to be the number of red points, right? Because the black points are labeled after the red points. So so these are the indices for the black points. Okay, so then lastly, so we can write this using an MPI or some sort of pseudocode for MPI. And then, so what this is going to do is we're first going to compute in parallel all of the red values. Okay, so XR is denoting all of the red values, right? And this is using the black values, but from iteration K, right? And then after that, you're going to do a barrier over here, right? Because you need to finish computing all of the red values for iteration K plus 1, right? So this collect elements here, this is going to include a barrier. And this is also going to take these values. It's also going to, so after you compute these values, you need to distribute them to these black points. Okay, so collect elements is also going to do that communication step. And then finally, we're going to do all of the black points in parallel. Okay, so here are the black points, and they're going to depend on these red values. Okay, so that's what we have for these iterative algorithms. So you can see that it very strongly depends on the structure of the problem that you have. Okay, so sometimes given a certain structure, we can somehow decompose the matrix for the we can decompose the matrix in a way that we can achieve parallelism. Okay, and other times because of this dependency in the Gauss-Seidel method, then you have very little parallelism. Okay, so then I'll see you guys next time.